Okay, so as we discussed previously, we would solve the assignment today, right? Let's look at question number 1. So design a buck converter with a source voltage of 50 volt and duty ratio of 0.6. Load resistance is 20 ohm. So let's start with question number 1. Okay, buck converter. With the source voltage of 50 volt, duty cycle of 0.6, load resistance is 20 ohm, maximum voltage ripple in the capacitor is 1%, so delta Vc is 1 upon 100 times the output voltage and delta IL is 5 upon 100 times the inductor current, 5%, right? The average of the average output current. So the average output current is same as the average inductor current, right? So ripple in inductor current is 5% of the average output current or the average inductor current. Assume CCM and Fs is given to you. Switching frequency is given as 2 kilohertz. What do you have to find? Okay, design a buck converter means essentially you need to, because so far, I mean, when you say design a buck converter, it's a more sort of broader word, right? Which means you design everything. But so far we know how to design the inductor, how to choose the inductor or the capacitor, right? So in this question, what is expected is you find the value of L, you find the value of C. Okay, I think this is looks straightforward, but we have not given you the answer, so you may not know whether you have done it correctly or not. But before we do that, right, few things. So if you see these values now, 1% and 5%, typically the output voltage ripple 1% is practical also, right? You would expect that kind of constraint. Sometimes it may be little less, sometimes it may be little more, but 1% a very reasonable value. But on the other hand, the inductor current ripple 5% is usually very, very low value. Ripple value is a very tight value. We usually keep it like 30%, 40%, those kind of values, right? Not 5%. The reason is because 5% is such a low value, it gives rise to a very large value of inductance, as you would of course calculate. But anyways, this is a question, so we have to solve it, right? So, any help you need in this question? Anyone? The answers we'll give you by end of today, right? But meanwhile, if you have any question, any doubt. Okay, what is the value of L and C that you guys are getting? It's, what was the L you got? 8? Yes, 8 millihenry? 18 millihenry? 80 millihenry? Yeah, this is like really, really large, right? This huge inductance, 80 millihenry is huge. So, what about capacitance? 1 molar. Go ahead. 15.625 microfarad. Is that correct? Is that okay? Okay, how many of you getting these values approximately? Okay, the other, do you want to discuss any part of it? You may have done a calculation mistake. Yeah. For capacitance part, can you, so his question is for capacitance part, can you use the formula? You mean this equation? You have to use it, no, there is no other, can you use, मतलब कोई option नहीं है उसमें. Oh, you missed the lecture. You have to draw the inductor current waveform, then you have to draw the capacitor current waveform. No, you know, fair enough graph, huh? Because this equation is linear equation, this ripple is small. So you know the inductor current is linear, right? The inductor current, what is duty cycle? 0.6. So let's say I try to draw it. So inductor current is like this, right? So you know what is the capacitor current? You know the capacitor current? So you would, the average will go there, so capacitor current would be like this, right? So you know you have to integrate from this point to this point to get the capacitor voltage ripple. No? This is something which we did in class. Any doubt? Still any doubt? Any question? Shall we move on to question 2? Okay. Okay, go ahead. Can you read the question number 2 yourself? Still a buck converter. $15 the forward voltage drop of the switch. So V switch is equals to 1 volt and V diode is given as 0.7 volt. So another buck converter, the question is find the output voltage of the following circuit considering the forward voltage drop of MOSFET is 1 volt and the forward voltage drop of diode is 0.7 volt. The switch is on for 40% of the time, so that means duty cycle is 0.4. The switching frequency is 5 kilohertz and it is assumed to be in CCM. So CCM and 5 kilohertz. So what is the, how many of you, okay, what is the answer? Let's write down the answer. What is the output voltage you guys are getting? How much? 5.18. How many of you are getting this answer? Okay. Any doubt? Those who have not tried it out or you are not getting the answer or you don't know how to solve it, do you have any question? Question bada? Read the question. Got the answer? Okay, next person, you read the question. Got the answer? Do you think you can solve it now? Do you want any input? Pakka? Anyone? Nobody wants any input on this? Yeah. So we have tried to simplify this question for you in a way, right? When you see the MOSFET, so MOSFET would have a channel. So again, you know, recall your course in which you have learned about MOSFET structure. You have learned about the lateral structure, right? Not the vertical structure, but even lateral structure, you would remember that there is a channel, there are these connections of metal with semiconductor, right? So when the current flows through that channel, there is a voltage drop. But how do you model it? Usually you would model it as a resistance. Why? Because you remember the MOSFET on-state characteristics, it looks like this, no? VDS versus IDS. Of course it does, IDS versus VDS. Of course it does saturate after a certain time, right? But assuming we are operating in this region, you can just model it as a resistance. So in reality, if you see when the switch is on, it gets modeled as a resistance, which has a finite voltage drop also. But then if we model it as a resistance, your equations become a little bit more complicated for now because then the drop depends on the current also, right? So just to simplify the question, in the question we have given you the voltage drop across the MOSFET, right? And similarly, the diode characteristics, if you remember, this is how it looks like, right? So it's a combination of a voltage drop and a resistive component, right? So diode usually you can model it as a voltage drop and a resistance 0.7 and I. If you push large current, the voltage drop will no longer remain 0.7, it will become more 0.8, 0.9, 1, 1.2 depending on the diodes, right? So in reality there is drops which are modeled as a combination of resistance and fixed voltage source. In this question we have only, just to simplify it and to give you a flavor of that, we have only told you that these are fixed voltage drops, right? So now you write the inductor voltage when the switch is on, KVL, the inductor voltage when the switch is off through diode KVL, and then make sure that average inductor voltage is 0, which will give you this answer. Is that okay? Any question? Anyone, feel free to ask. You want me to write those equations? No one wants to ask anything? Okay, and let's go to question number 3. Question number 3, can you please read and see if you, oh, there is no question. Consider the following circuit. There is a question. Let me first draw the circuit, then we will go to the question. What is this circuit, by the way? What is this circuit called? Buck boost? Kind of buck boost? Not actually buck boost? Okay, let's scroll down to the question. Yeah. The minimum current of the inductor is 0, but never for a finite duration at steady state. Find the peak value of the inductor current and also the duty ratio. So let's go one by one. First of all, this circuit, you are seeing it for the first time, or we drawn it in the class before? Not in our class, right? Okay. So as far as this class is concerned, you are looking at it the first time. What is this circuit? How many of you have idea what is this circuit? Just raise your hand so that I get a feedback. Okay, very few. This is a buck boost circuit. This is a buck boost circuit, right? How it works is that switch on, when the switch is on, this is on, right? This voltage is positive here, this is negative here, right? And therefore the diode voltage will be reverse bias by 500 plus 100, right? You see the diode, if the S is on, the diode is reverse biased by 500 plus 100, 600 volt, right? So diode is not conducting, switch is on, the inductor current would rise, current will flow in this loop. When the switch is open, this current is flowing down, it cannot flow through this loop, so it would force the diode to become forward bias and start flowing in this loop, and that's how it will charge the output capacitor or whatever you have at the output, right? Current will start flowing in, so this will get charged. May have a capacitor resistance combination here, which is the normal buck boost. In this case, what we are showing is we have put a battery there. So it's like we have taken from one battery or one voltage source, putting current into another voltage source, right? Instead of this, you can have a same output capacitor and with parallel resistance as we have done before, and the current sort of falls down, right? So that's a buck boost. Why that is buck boost? Because if you derive the expression for average inductor voltage equal to 0, if you make average inductor voltage equals to 0 in this case, you get the output voltage upon input voltage as D upon 1 minus D, right? So if you see this expression, if your duty cycle is 0.1, the gain is 1. If your duty cycle is less than 0.5, it behaves as a buck circuit. If duty cycle is greater than 0.5, it behaves as a boost circuit, right? So you can choose, the circuit remains the same, you can choose the output voltage, you can adjust the output voltage, or if your input is varying, you can maintain the output voltage by varying the duty cycle. What is having lesser voltage? You don't know what will be the inductor voltage. If you don't have the diode, what will be the inductor voltage? If you don't have the diode, or if the diode doesn't conduct, what will be the inductor voltage? No, if you don't have the diode, and if the switch is open, what will be the inductor voltage immediately after the switch is open? The same principle, no? If there is no diode, when the switch was on, this is how current is flowing. When the switch is off, the current doesn't have any path. So V equals to L di by dt, current will suddenly become 0, you will have infinite voltage and the polarity, and that would force this diode to turn on. So not inductor doesn't have more than 500 or less than 500, infinite. I mean, if it doesn't have a path, it will have very, very large voltage, na? So this voltage doesn't really matter once you have inductor in picture. The value of that doesn't really matter. Any other question? Okay, so is this clear, buck boost converter? There is going to be a question in the quiz on buck boost converter. So make sure this is clear to you. I may be joking also, I may not. So is this clear to you? Anyone wants me to repeat this part? No, feel free. If you want me to repeat once again, I would do that, no problem. Is buck boost okay? Okay, now the only difference you see from the usual circuit is that here we have connected a fixed output voltage battery and a fixed input voltage source, right? Which is what it makes this little bit sort of difficult from the previous circuits that we have seen where we were connecting an output capacitor and resistance. Here also you can do that, but we have done it this way. So now the question is that all these things are given, duty cycle is also given, no, duty cycle is not given, but you know input voltage, you know output voltage, you can calculate the duty cycle. What do you get duty cycle in this case? What do you get output? If output is 500, input is 100, what do you get? 5 by 6, okay, is the duty cycle. So you have duty cycle, you have to find the peak value of the inductor current such that this is operating in a critical conduction mode, right. So it's already written there, the minimum current of the inductor is 0, right, but it doesn't stay at 0. So that means it's a critical conduction mode, right, this way. So now you have to find the peak value of the inductor current. You can apply V is equals to L di by dt during this period, right. You know the voltage getting applied across inductor, you know the duty cycle, you know the frequency, you can find the peak current. Is that okay? Any doubt? Any question? Okay, how many of you understood this? Raise your hand. Okay, those who have not understood it, why don't you ask some question? Pucho? Anything? Nothing, right? You got in the trick, you didn't raise your hand, huh? No question? Okay. So if you see this buck boost converter, there is a small problem here. The problem is that if you consider this to be ground, right, if the input is grounded at the negative side, output you get is actually minus 500 and not plus 500, right. So this buck boost, you know, in a way flips the voltage polarity also. That also again may not be desirable at in some applications, may be okay in some applications. But you know, if anyways you have to go from 100 to 500, you would not use a buck boost, you would just use a simple boost. Only if your input varies, let's say input varies from 100 and goes up to 1000 volt, right. Depending on something, input is let's say a battery, the voltage is varying significantly, hypothetically. Then you can use this circuit and you can, you know, you would use it. Otherwise, if input is always 100, why would you use that? You would use a boost instead of using a buck boost. Shall I erase it? Any question here? No question? Okay. Let's go to the next question then. Why don't you read question number 4? A buck converter, again a buck converter. With a source voltage of 100 volt, duty ratio of 0.4 and the output voltage is 50 volt, given values of L and C is given to you, Fs is also given to you. Find the peak value of the current, find IL peak. Second part, find the average output current, which is nothing but equals to the average inductor current, because this is a buck converter. Okay, I think this is straightforward, right? You have already done how to calculate the peak current and the average output voltage in a buck converter, right? So what is the answer? What is the peak current? Anyone got the peak current? 5. And what about the average output current? 2, 2.5, 2. How many of you got both the answers? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. What about others? How many of you tried, didn't get the answer? That's a question. How many of you tried and didn't get the answer? Oh, no one. So that means whoever tried got the answer, right? So that anyone who tried and didn't get the answer? Okay, then that means it's not a very difficult question. Why don't you guys try it now then, those who have not tried it? Go ahead, solve for it. You know the answer anyways. You know the question. Why don't you try it? Maybe you'll use this time. Yeah. So try it. Correct. So try it, right? That's what I'm saying. Okay, so one thing you should be really careful about is that any circuit, if you see, check and make sure that is it operating in CCM or DCM, right? That is the first thing you should do. Don't just blindly assume that if a circuit is given buck converter dikha and then you just start applying your formulas, right? Don't do that. First check if it's in CCM, DCM. Most of the question itself may mention, assume CCM or it's in CCM or something, but not 100% of the time, right? So for example, in this question, of course, it's not clearly mentioned it's CCM or DCM, but if you see these three values, doesn't make sense together, right? So if you use 100 volt 0.4 buck converter, output should be 40, but output is 50, and we know that whenever it goes to DCM, the output voltage is more than the corresponding CCM voltage that you should have got. So therefore, output is 50. So first thing is you conclude it's a DCM. If you conclude it's a DCM, I think then it sort of becomes straightforward, right? So your inductor current will be like this. This is D times Ts, this is gamma times Ts, and this is Ts, right? You know the output voltage, you know the input voltage, you know the duty cycle, you can find the value of gamma from here, right? How much gamma comes out to be? 0.8. Okay, so you can find the value of gamma. Once you know the gamma, then you can, anyways, for finding the peak, you don't need gamma, you know DTS, you know the applied voltage, V equal to LD parity will give you the peak value. You can find the peak value, and to find the average of this one, you require gamma. You can find the average of this, and that is nothing but what would be the average inductor current, which is same as the average load current, because the average capacitor current is equals to 0. So you should get these answers. Okay, any doubt? Question number 4. Okay, so question number 5, you have to, assuming CCM, you have to draw multiple waveforms for buck, for both boost as well as buck boost. I think this is something which you can do now, given that now you know what is a buck boost converter, right? So, question 5, you can just read it quickly and let me know if you have any doubt in question number 5. Any questions? Okay, then let's move to the quiz questions. Quiz 1 questions. Question number 1, you have been given a diode rectifier. Inductor value is sufficient to make the inductor current to be continuous. That means IL never becomes equals to 0 for a finite duration. Draw the input voltage, output voltage across R and L together, and the inductor current waveform in the same axis, right? So, if this is your input voltage, right, of course you don't get any mark for drawing the input voltage, just to be clear. So, next is the output voltage. If you see, the output voltage is across the combination of R and L, right? Let me quickly draw the circuit here as well. So this is your output voltage, right? So an inductor current is always there, it's never 0. So initially when this input voltage is positive, right? These two diodes, if you see D1 and D2, which of the diode will conduct, D1 or D2, when the input voltage is positive in the first half? D1 will conduct, right? And why would D1 conduct? Why will D1 conduct? Yeah. In the first half, when the input voltage is positive, somebody said D1 will conduct when the input voltage is positive in the first half. Why do you think D1 will conduct? Why? No. Next person. Yeah. If D1 is not conducting, then a little bit louder. Anode side has some positive voltage with respect to the ground, okay. Cathode is not grounded, cathode is here, ground is here. Cathode and ground are, current may flow through some other path, no? There are other paths also. This current can flow through other path. Inductor current is continuous, it can flow through some other path, no? Next person. Okay, assume if D2 is conducting, okay, okay. But why D1 should conduct? Why not D2 keeps conducting? Next person. Next person. At that point, when the current becomes 0. Yeah, but it will not wait for the current to become 0. You are right, you are on the right track, but it will not wait for the current to be 0. What he is saying is, if D1 doesn't conduct, then D2 is conducting. This current is of course decaying because there is an RL circuit. When this current becomes equal to 0, then D1 will start conducting. Bol bhai, want to add something? Want to add something? Go ahead. Why will D1 conduct? Simple question. Why will D1 conduct in the first half cycle? Current is flowing already. Current is non-zero, so current is flowing in the inductor. Yeah, but how do you know V in becomes more than this voltage? I have drawn it correct, I think, but wait, आ जाएंगे, वहां पे भी आ जाएंगे, don't worry. I think we should clap for him. And genuinely, I mean, I was so surprised how could a lot of you did not answer it, na? This cathode point is common. So wherever anode has higher potential, it would conduct. This is something which we learned in the first class or something, right? क्या कर रहे हो यार? Right? Yeah, common cathode configuration. So whichever anode it has higher potential, it will conduct. In the positive cycle, this anode is at higher potential than anode 2. This is plus, and the minus is directly connecting here. In the negative half cycle, this is at a higher potential than this. So in the negative half cycle, this will conduct. Right? So positive D1 will conduct, negative D2 will conduct. Okay, so what will be the output voltage? And then after this, when D2 is conducting, the output voltage is equals to, when D2 is conducting, the output voltage is equals to, go ahead. D1 is fine, right? Then this is the region when D1 conducts, this is the region when D2 conducts. When D1 conducts is okay. What about the next cycle now? D2 conducts, then what is the output voltage? Waveform? What is the output voltage waveform? Next one? 0, no? Yeah. Is that okay? Okay, let's hope you have done it correctly in the quiz. It's simple, right? Diode circuits, you have done it, and this is how the output voltage would look like. Any doubt in this one? When D2 is conducting, what is the output voltage? D2 is conducting, this is short, so output voltage is 0, right? Is that okay? It's anyways given to you in the question that the inductor current is continuous. So inductor current, now let's draw the inductor current, next step. Can you draw the inductor current? Approximate inductor current, can you draw? Can you draw the approximate inductor current? Okay, let's look at this region first, right? There is no question in this region your output voltage is 0, so inductor current will drop because of RL circuit, right? So let's say approximately it is going down like this, okay? Not exactly straight line, RL kind of response. Fair enough. So in this region it should increase, right? In these regions, if you see in the beginning and towards the end, your input voltage, this voltage is positive, but your I into R drop could also be substantial, right? So it may still be decreasing. So this may again, be maybe still falling, but then this would go up and then maybe, again fall a little bit. So something like that is what I would guess. Approximately, right? Of course, you can write the equations for different region, you can find out, but this is how I would think it would look like. Anyone has any other opinion? So the way I am thinking is here it's anyways falling. In the beginning and the end region, right? How much region of course depends on the equation and the values, exact values, but roughly in the beginning and the end region, this input voltage is very small, but there is an I into R drop. So voltage across inductor would come out to be negative. So it should still fall some way. So I have shown it as falling, and then in between it's sort of going up. Right? So roughly this is how it would look like. Of course, you have to draw it such that the starting point and the ending point is matching for this operation to be at steady state. Okay. A part is okay. Any doubt in part A? Question number, now part B, find the average value of inductor current. Find the average value of inductor current. Right? How will you find the average value of inductor current? You write Kirchhoff's voltage law and you can say that the output voltage is equals to IO or IL into R plus L times DIL by dt, right? You can write the output voltage as this. Do the average on both sides, right? Take the integral dt of all three, right? And 1 upon total t, 1 upon total p, 1 upon total p. Correct. So if you are in steady state, last integral will be equals to 0 because the starting inductor current will be same as the ending inductor current, right? So the average, so therefore this is a separate block. So therefore you get that integral of this one, which is nothing but the average output voltage, is equals to resistance times the average inductor current. So you know the average output voltage, you know the resistance, you can find the average inductor current, right? Is that okay? Any question? So you can find the average value of this inductor current by this. Any doubt in question 1? Anything you want to ask in question 1? Go to question 2 then. Okay. Can you read question number 2? Okay, what is the answer to question 1? Let me give you the answer first before we move on to question 2. The answer to question 1 is 1.0 0.03 ampere. Maybe, I don't know. 1.03 ampere is the answer for question number 1. Let's go to question number 2 then. Why there is no question number. Yeah, let's go to question number 2. Draw the input voltage waveform and output voltage waveform such that the output voltage follows the input voltage till 30 degrees after the peak value of the input voltage, right? This is your input voltage waveform. If you had only resistance, your output voltage waveform would have been this half, first half and then 0. If you had a pure capacitor, it would have been rising with the voltage and then would remain constant. In this case, we are saying it continues to follow this waveform 30 degrees past. So, this is 90, this is 120, and then after that, of course, it decreases with the RC constant, and I don't know what happens to that. Maybe it touches here, maybe it touches here. It will never touch actually. So, it will sort of keep going like this, and then again it follows the same one. So, this is answer to part A. बोलो 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 क्वेश्चन तो बताओ. Maybe practically yes, may not be theoretically. Okay. So, part A is fine. Any doubt in part A? Then part B, calculate the value of C to achieve this condition given in part A. Right? How do you make sure that the voltage follows, the output voltage follows the input till this point and then it detaches? This is something which we have discussed when we have discussed it just before the quiz on the same day, right? Because there was a question in assignment and I think somebody asked the question and then we did discuss about it. So, if you had a very small value of cap, right, then this kind of thing can happen. Not very practical. We would not usually design the circuit to be like this way, but it can happen if your capacitance is very small, right. So, the question is how do you find the value of C? So, from going from here to here, right, if you see this 30 degrees, if your RC discharge is very fast, right, then only this diode will turn on and your this voltage will be clamped to the input voltage. If your RC discharge is very slow, then this voltage which is going fast down, this voltage will not go fast down. So, you have 3 options, option A, option B and of course, what actually happens is option C. So, if A is the case, then output voltage will follow A, right, if your discharge is very slow. If your discharge is very fast, then you think you should be at B, but you can never be at B because if it discharges fast, this will pump up. It will discharge fast, this will turn on. So, this circuit, it's also called as clamping circuit, a terminology which not necessarily you should know, but this is also called as clamping circuit. What it means is, it would never allow this voltage to fall below this voltage. So, it would clamp this voltage to this voltage, right. So, if it tries to fall, this will make sure that the voltage is just following. So, what happens is at this point when it gets detached, at that point if the diode is off, the slope of this, and if the diode is on, the slope of this capacitor is almost same. And before this, the slope of voltage following in this circuit is much more than the slope of the voltage following, and after this the slope reverses, right. So, at this point the slope of this circuit and the slope because of the input voltage are matching. So, dVc by dt coming from this circuit should match dV by dt coming from this circuit. Is that okay? That is what would give you the point of separation. Any question, any doubts so far? Any questions? No questions? Do you want me to do the next step? You have to differentiate. This is anyway sinusoidal voltage, you know, 325 sin omega t. So you can differentiate this. This is I equals to C times dVc by dt. So dVc by dt is IC by C. What is IC? IC is the voltage at that point divided by load resistance into C. You know the voltage at 30 degrees, so you know the slope if this diode turns off, and you know the slope if the diode remains connected, which is the slope of the sinusoidal. Once you equate the two, you solve it, you will get an answer. Right? No? Want to repeat again? Yeah? You require the values, yes. So you know the voltage, you know RL, you know C. Sorry? You would equate the, you would equate the slopes of both the systems, right? You would equate the slopes. Slope of this circuit is nothing but given by I by C. Immediately at detachment point, the voltage is almost the same. So V by RC, you know the voltage, you know R, so you get an expression in terms of C. On the right side, you know this is 325 sin omega t. So again, you know the slope at that angle 120 degree. If you get the two, you would just get quickly value of C. I think that should be very straightforward, na?
So why are we equating the slopes? Because I think we should equate the voltage at 120 degree voltage because the value at that point is same, right?
Okay. Okay. Okay, we'll come to that. Just give me 1 minute. But first, let me gather all the doubts. By the way, what is the answer? 5.51 microfarad. Okay. So anyways, let's note down the answer. I will come back to this question. 5.51 microfarad. Okay. Any question? Any doubt? What he is saying is, why are you not equating the voltages at this point? Why are you equating the slopes at this point? Why are you not equating the voltages at this point? Right? Yes, we are, of course the voltages are equal, there is no question, and we are using that. Voltages are equal, in addition the slopes are also equal. If you use both of them, then you would, solve it very, very fast, of course. Voltages are of course equal, you can see it, voltages are equal. There is no problem in that. In addition, the slopes are also equal, that is the main point. So if your question is why slopes are equal, I can answer. Why voltages are equal? Of course, all of us agree voltages are equal. Voltage equal will give you one condition, will not be sufficient enough to give you the value of capacitance. Yeah. Yeah. Voltages, no? But they are equal, na? Okay. That's what he meant. You can't equate means you will not get anything new, maybe that's what you mean, but they are equal, na? You can write this is equal to this, that's fine. But you would not get any condition out of it, that's what maybe what you mean, right? Okay, jokes apart, any other question? So question 2 is okay, any doubts? Oh, doesn't appear here. Let's go to question number 3 then.
Like at that point, let's say discharge चालू where you are not seeing, let's say exponential discharge चालू है.
Correct.
So this point का slope how is it equal to the sinusoidal slope?
Because before that point, one slope was more than that. Okay, that's a good question. Let me just think over it. So what we are saying is, before that, at all the points, one slope was more than the other, right? The sinusoidal slope, sorry, the RC slope was more than the sinusoidal slope. More, RC slope. If the diode turns off, the RC slope is more. That's why the diode is never turning off. Yeah. After this point, the RC slope is less than the diode slope. And the derivative is continuous, right? Why not? The derivative, even if you find the second derivative, it is smooth, right? So, can't that be used to make sure that at this point both the derivatives are equal? You can do that. No?
The actual waveform follows the sinusoid till 120 degrees.
Correct.
And then from that point discharge चालू होता है with exponential decay.
Correct.
So वो exponential decay का slope how is it equal to sinusoidal का slope? Because I think it's non-differential.
Yeah, but no, but we are not saying that. What we are saying is, till that point, we are not differentiating that particular curve. What we are saying is, just after that point, the slopes will be equal. Think of it this way. Because if you don't have this, then you can write the slope equation for this, which is differentiable, which is continuous, everything is perfectly fine, right? Before this point, everywhere this slope is more than this slope, or it's steeper than this one. And after that, this is lesser steeper than this one. So, wouldn't that be sufficient to say that at that point, that slope is equals to that point? Especially if it's, it's continuous, its double derivative is also there, that's also continuous. Good point. Why don't you guys do a small simulation and check? Of course, this is something which I asked you before also, right? You must try to use some simulation tool, whichever you are convenient with. Try to build this circuit, try to plug in these values, and then see for yourself, right, what happens. Yeah. Only thing is, when you are doing simulation, you cannot just leave all the thinking to the laptop. You still have to think. The reason I am saying is because when you simulate this circuit, the simulation elements may have some hidden resistances in some of these guys, right, which they would use to get a simulation done. But then you may feel like, look, I have not added any extra R, but this is not matching with what sir said. So of course you can ask me, but before doing that, you think, there may be some other things in simulation which you don't know. So do simulation with thought, I mean, you have to continuously think with the simulation. Don't think that you would do the simulation and it will just give you the answer. Whatever it gives you is the correct. That is not how the simulation works, right? It only helps you. It doesn't tells you what to do in a way, right? Okay, let's move to the last question now. Otherwise, we won't have sufficient time to distribute you the question papers. So let's move to question number 3. This we have discussed in even 114, right? Even in 114 have we discussed this, how the fan speeds are regulated? No? But we know what a fan is, right? Or at least what a conventional fan used to be. That we know, right? It's a single phase induction motor, right? How you can change the fan speed? There are multiple ways of changing the fan speed, right? One is that you can inject some resistance in series, right, which would create an IR drop and you would lead to a lesser voltage at the winding terminal, right? So you can put a series resistance and which you can keep changing as you go from speed 1, 2, 3, 4, 5. The resistance can be slowly removed from the circuit. So at 5 speed, you directly connect the input voltage to the fan. At 1 speed, you have a large resistance in between. That's one way. The other is you can replace, instead of using the resistance in between, you can put capacitance in between, because anyways, this is a AC circuit. So the drop was created by resistance. Capacitor will also create a drop. But in addition, capacitor will not have any I square R losses, right? So you can do a capacitor switching. This is what most of the regulators these days would have. The third option is you use the semiconductor devices like this arrangement, which is basically in this drawing you look at it as two thyristors, but in reality this is a single device called triac, right? A single device called triac, and that's the question. So what is given to you is the firing angle. If this is your input voltage, you fire one of the triac at this point, another triac at this point. It's resistive. So before the triac is fired, since there is no inductor here, there is no current flowing here, so this is 0 volt. If there would have been an inductor, there may be a current flowing and this may have been non-zero, but since it's pure resistance, 0 volt at the output. As soon as the triac is fired, the input is positive, your output will become equal to the input, then it will follow, it will go to this point. After this, what happens? After 180 degrees, what happens? Your output voltage follows the input or it becomes 0. Follows the input or becomes 0. And then at this point, the other triac is fired, which is the second one. Now you understand this voltage is negative, right? So this was the reference polarity. Now this is negative. So therefore, if this is fired, again this circuit is connected. So the negative voltage will appear across the output. So your output will have this. So you see, this is not a rectifier circuit, right? It's not a rectifier circuit. Your output voltage is still AC. But only thing is the RMS value of the output voltage is now reduced as compared to the previous case, right? So if you keep increasing the firing angle gamma or whatever you want to call it alpha, if you keep increasing the firing angle alpha, your average or the RMS output voltage will keep reducing and the fan speed will keep reducing as well. So those speed regulators where you can do a continuous speed control, na? You have seen, some regulators have tuck, 1, 2, 3, 4, 5 and some have this continuous control. So those which have continuous control would have this kind of thing in it. Those who do tuck would have most likely the capacitor switches network in it. You can, you can just open them. The capacitor one is very obvious. Once you open it, you will see, 2, 3, 5 capacitors connected in that block. Is that okay? Any question? Answer? What is answer for? So you have to draw the voltage waveform, find the RMS voltage. What is the RMS voltage? Answer क्या है भाई? 226. Okay. So as this final answer is very close to 230, the accuracy of the final answer may not really matter most, but the waveform and how you arrive, the expressions that you write for finding the RMS would probably determine your marks. Any questions? This we can stop.